So I think you're able to see my screen.
Yes, sir.
Yes, sir, it is visible.
Okay. So 1 minute. I should show my video. Then muted. Class 4. Okay, are you able to see now?
Yes, sir.
Okay, so try to understand. Okay, if any problem, you let me know. Okay, this is maybe the second year student, they can find it is difficult, but it is not so difficult. So try to understand the things. Okay, slowly. Okay, so today we are discussing the experiment number 3. Okay, experiment number 3, the direct shear strength test to find the shear strength parameters like cohesion, friction angle, dilation angle, and shear strength of jointed rock. I think you understand the difference between rock and rock mass. Is it clear? Anyone? What is the difference between rock and rock mass?
Sir, rock mass is those rock present on situation like in situ rock masses. Rocks are called rock mass, and rock is a particular testament. Like we create a sample in the rock mass and take it to the lab to test it.
Okay, so you want to say rock mass contains the n number of discontinuities. Okay, so today
Yes.
we will discuss about joint. Okay, and what is the shear strength along this joint. Okay, so this is our today's lab. What is the shear strength along that joint? So I will give some brief. Okay, so if you see if I want to define it, okay, so joint can be defined as a line of break of geological origin along which there is no visible displacement. Okay, if I say there is a visible displacement, then what will be it? Then what is the category of that? It will be joint or something else. Are you following what I am telling? What is written here? Break of geological origin along which there is no visible displacement. This is the definition of joint. If I say there is a visible displacement, then I can say it is joint or not.
So if there is a visible displacement, then we can't say it as a joint.
Then what will you say?
So it will be a fault, like there are different.
It will be fault. Okay, if there is a visible displacement, then it will become a FAULT fault. So we are not discussing that. Okay, joint may be opened or filled. Opened means there is no filling material. It can be filling material like calcite, gauze material, quartz. Okay, it can be there. Okay, so if I study the joint, suppose if I'm making this is your intact rock. Okay, I say this is intact rock. Suppose in this rock there is a one joint is there. This is one joint is there like that. Okay, so this joint has some roughness. Okay, so how we define the roughness? Roughness of joint surface composed of first order. I will explain later on. First order, this is called waviness. If I say this waviness, okay, and second order unevenness of the expertise. Unevenness means if I say the little tiny expertise will be there. Okay, so that is defined as a unevenness. Okay, so I can say first order and second order expertise. This is the definition, classical definition of the roughness. Okay, now joint parameters affects the overall shear strength, deformability behavior, in situ stresses, and hydrogeological properties of rock mass. Okay, what is the meaning of that line? Suppose this is the intact rock. Okay, so it will fail. If you do the UCS or triaxial test, you will know how it fails. But if there is a joint, so there is a maximum chance that it will fail along this joint plane. Okay, so I should very much interested to find the shear strength along this joint plane. Okay. Now, shear strength of rock mass is important design parameter in mining, excavation, dam foundation, power plant, underground caverns, and slopes. Okay, so we apply these are the input parameters. We, if you want to do numerical modeling, we apply these all input parameters. Okay, this is a brief. Okay, nothing to worry about it. This is the only brief. Okay, so if you see this picture, okay, what is shown in the first picture? There is just some three set of joints are there, and this is, if I say this is one joint. Are you able to see this? Are you following what I am telling? Yes or no?
Yes, sir.
Okay, if you see there is a n number of joints, okay, there is a one joint here, there is a one joint here. Okay, so I am interested to find the shear strength along this joint. How to find this? This is the experiment. What is the implications of that? If suppose there is a landslide at Bingham Canyon mine at Utah at 10 April 2013. Okay, so this landslide occurs. Okay, why? Because the shear strength along that plane is so less. Okay, so that's why the landslide occurs. So to study these problems, we want the shear strength along the joint plane. Like you can say there is a wedge failure. Okay, there is a wedge failure. So along that plane, along this plane, what is the toe I want to calculate? Okay, any questions so far?
Sir, in the first picture, we are seeing that there are some lines. So what is this visibility mean, sir? Aren't they visible to us that they are there is a line between them? That
Yeah,
visibility or anything other than that?
these are the joints, na? All lines are the joints.
Sir, here it can't be a fault, sir.
No, no. Fault, it means you will be there's a visible displacement. Okay. If you see the in geological book,
Displacement.
na, it is
Okay.
you cannot say it is a fault. Okay. Joint is the break. Only the, suppose this is the joint, this is the rock, na, only the break. You can see in any structure, okay, any rock. Okay.
Okay, sir.
Clear?
Yes, sir.
Okay. So as I discussed in the first slide, so suppose this is the roughness. If I say this is joint, this is my rock, okay, and this is roughness. So how the people have defined this is again we are concluding with the ISRM statement, okay. So if I say this is the roughness, okay, so this is the waviness. See the definition. Waviness means the sine curve like that. This is the waviness, okay, and the small one will be the on this small expertise will be there. Expertise means roughness. I'm talking about roughness. So this is will be the my secondary expertise. So what we do in the lab? What is written here? We'll take out the sample from there, like 10 centimeter, okay, like 20 centimeter, 30 centimeter, okay. So we are what we will do today, we will only discuss the 10 centimeter rock joint sample, okay, for the laboratory test. There is the another test is there which is called in situ shear stress test that we do in the field. So we are not discussing that one. We are here only discussing the laboratory shear test where the size of rock joint is 10 centimeter, 20 centimeter, 30 centimeter. Okay, today we'll discuss about the 10 centimeter rock joint sample. Okay, so now if you see, so I think you know what is the cohesion and angle of friction. This difference should be clear. Okay, the interparticle forces of resistance which holds particle together in soil mass. You can say rock. Okay, you just here say rock mass because we're talking about rock, not soil. Okay, this depends upon the shape and structure of the molecules. You can say cohesion means this is the how can you define cohesion? Anyone? Please speak something.
So cohesion is the physical property of any surface which resists its motion opposite to which resists opposite motion, relative motion.
Anyone else other than you? I think there are
So sir,
166. Yes,
it's
Boli.
kind of both. The cohesion is like a binding force, which is like resisting the motion of the particles.
Okay. Then what is the angle of internal friction? Anyone? What is written here? The resistance developed due to the friction between individual particle at their contact points due to interlocking of particles. We discussed the phi. Okay, you should be very clear with the cohesion and angle of internal friction. I think anyone has the doubt for these two definitions, please let me know. Okay, no doubt? Yes or no?
Sir, what is the difference between them, sir?
Difference between?
Sir, cohesion and angle of internal friction.
That I'm asking now. What you understand? You tell me first.
Sir,
What is
both
written
are.
here? Please speak.
So both are they are internal force part kind of thing. So force of resistance that is written in both the definitions.
Listen. Suppose this is your rock. I can say rock is made of some grains. Can I say
Yes,
like
sir.
that?
Yes, sir.
So in between grain, okay, there is some binding force, okay, that we represent by the interparticle force, okay, that is defined by the C, okay. And
Yes, sir.
what is the angle of internal friction? When the suppose all are the grains, when the shearing occurs, okay, so what will happen? The resistance developed due to the friction between the individual particles. So what will happen? The particle will ride on each other, okay. So that will create some friction at the time of shearing. That is called the internal angle of friction. I hope it is clear.
Yes, sir.
Okay. For today's lab, the laboratory methods for shear strength of rock joints. Basically, what we do in the laboratory, there are two schemes. Okay, we do test in the lab. Okay, first is called constant normal load condition. This is called in brief CNL condition. Okay, try to understand this one. Like is the free movement of rock slope and dam foundation. I think you know the slope. Okay, this is a joint plane in the slope. Okay, and this is the weight W. So when this W weight will slide, so I can say this W is always constant. Okay, on this joint plane. So that's why I'm saying the constant normal load condition. It means during the shearing, my normal stress, normal load will not change. Okay, like if you see here, this sigma n. Okay, throughout the shearing, this is my joint plane. If it is shearing is going on, this sigma n should not change. It should be constant. Okay, that's why it is called constant normal load condition. Okay, so what is happening here? The toe is the shearing will occur on this plane. Okay, 1 minute. Hello. 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 Okay, so this is called constant normal load condition. What I say during the shearing, the sigma n normal stress should be constant throughout the shearing, like as I discussed in the slope. Okay, now you see the another case. This is called constant normal stiffness condition. Okay, suppose there is an underground excavation. Okay, and here is the some joints are there. So what will happen? Naturally, this block wants to come out from the roof, but the surrounding rock is prohibiting that one. Okay, I can say the surrounding rock is limiting that block to come out. Okay, so why it is happening? Because this surrounding rock stiffness, I can say the stiffness of that rock, stiffness of the surrounding rock is not able to, is not allowed the rock to come out. So in that condition, what will happen? Your sigma n will keep changing, because what will happen, this block wants to come out, but this force, the surrounding rock will, the load on the surrounding rock will be applied, so the sigma n is not constant there. Okay, so this is called constant normal stiffness condition. Okay, so
So
this
can you
is
repeat it once again?
please ask me.
So can you repeat this constant normal stiffness condition?
Okay. Listen. Suppose there is a underground excavation is there, okay? This is a jointed rock mass. Suppose I'm here making here. This is the underground excavation I'm making. And suppose a number of joints are there, okay? Because I'm making the design in the rock mass. Okay, so what will happen? This is the cross joints. Okay, so this block will fall. Definitely should fall by the gravity. Yes or no?
Yes, sir.
Okay, so why it is not happening? Because the surrounding rock stiffness. Okay, that is holding this block. That's why it is not falling in the underground. So it means the stiffness of that rock is play the role here. Okay, if you see here, there is no surrounding rock is limiting this block to slide down. It will slide along this joint plane. But here the surrounding rock will stop it. So we define in technically this is the stiffness of the rock. You getting my point?
Yes, sir.
So here what will happen if stiffness is playing the role, so your sigma n is no longer will be the constant because your block wants to come out, but this surrounding rocks will not able to do it. So your sigma 1 will be increased in that way. So this is called constant normal stiffness condition. In this lab, today's lab, we are only follow this CNL load, normal load condition. Okay, we will not do CNS condition here. Only CNL condition we will do. Okay, the graph we will explain later on. I think things are clear. Can I move forward?
Yes, sir. Thank you, sir.
Yes, sir.
Okay. Now, if you see the shear properties, okay, first I want to make you clear, okay, if there is a one intact rock and another is a some jointed rock. So in this experiment, I am very much interested to find the properties along this joint plane, okay, along this joint plane, C, phi or tau. Okay, along this joint plane, these are the properties, Cj, phi j, you can say. Okay, in next experiment we will do triaxial test, then that will be the property of intact rock. So I'm not talking about the intact rock, I'm talking here about the property of the joint plane, along the joint plane. Please keep in mind these things. So what can I find from this? Peak shear strength, residual shear strength, we will discuss all these things. Cohesion, peak friction angle, residual friction angle, these things you have to find. Basic friction angle, peak dilation, shear stiffness, normal stiffness. So for today's experiment, we have to find number 1, the peak shear strength, 2, 3, 4, 5. No, it will not be there. Peak dilation 3. So you have to find 1, 2, 3, 4, 5, 6, 7, 7 parameter. Okay, I will explain how to find it. Okay. These are some theory, okay, just be patient, okay, otherwise you will recover in this theory, okay, you will read in the theory, basically the second year student. Okay, suppose if the what I said, the joint have some this type of structure, this is the first order and second order expertise. Okay, what Patton has done 1966, he has made the teeth type of structure, he idealized, he the simplified. Okay, he said we make the joint in this fashion. Okay, I can say this is sawtooth specimen. Okay, simplified, he make the joint in a simplified way and put this is called CNL condition. It means sigma n is constant and this block is fixed. Okay, I am moving it. Okay, and this angle I can say 20 degrees, this is called asperty angle. If I say this is, so this angle is given that I. This is theory, okay? I'm just explaining you what is happening. Okay, so suppose if there is no roughness, if I make it very clear, okay? If I circle the roughness, this is a smooth joint, totally smooth joint. So what can I write? What is Mohr Coulomb? If you see Mohr Coulomb, C plus sigma and tan phi. This is Mohr Coulomb. So along if there is a joint plane, I can say C can be 0 because there is an open joint. Okay, there will be no C. I can write here the for plane joint tau equal to sigma and tan phi b. Phi b is called here basic friction angle. Okay, because there is no roughness. If there is no roughness, that angle will be the basic friction angle. Okay, but if there is some type of expertise are there, then he defined the angle sigma n tan phi b plus I. I is your this angle, expertise angle, as I discussed. But as soon as I increase this sigma n, okay, what will happen? Can you tell me what will happen? If I increase this sigma n, then I'm making the shearing of this block. Some expertise will be sheared off. उस break होगा.
Yes, sir.
Okay, that type. Then if I make, then I will say there is some cohesion should be there. The expertise is breaking there. Then pattern has said there should be some cohesion. Cohesion of for this rock. The rock टूट रहा है, whatever the rock is breaking, that have some cohesion. That's why C is there, sigma n is there. So I can say this is at higher normal stress. This will be at lower normal stress. Okay, because at lower normal stress, the expertise will not break. Okay, it will ride. Okay, at higher it will be break. So I can say C plus sigma tan phi. So if I make the envelope, if I draw the graph, so then it will be C. Here it will be C and that will be phi. So what we have to remember here, when we are increasing the sigma n, there can be some cohesion. Okay, according to pattern. Okay. Okay, then it will be phi. If there is a low sigma n, then I should write is sigma n tan phi b plus I. I hope something you get from this graph. If you are not getting, then don't worry, you will recover in the theory. Are you getting something?
Yes, sir.
Yes, sir.
Okay, good. Then again some theory, then pattern Barton 1973 and 1976. Okay, what he said, the shear strength along the joint, okay, it is should be given by three parameters. Three parameter means, suppose this is the roughness. So first is phi b, when there is no roughness. Phi b matlab there is no roughness. Okay, smooth joint. Then there should be some dilation angle, and this is the damage of the expertise. Okay, so if you go to those papers, then you will find here given this equation sigma n tan phi b and JRC log 10 JCS by sigma n. Now if you are comparing with this your Mohr Coulomb tan phi, okay, so again along the joint the C should be 0 because this is open joint. We are not talking about the filling joint. This is C 0. So what you can say from here, this phi equal to, if you compare these two equations, what can you write? Okay, you can write JRC log JCS by sigma n. Can you write or not?
Yes, sir.
Okay, so this is called effective friction angle. Okay, so what do you remember? You remember Barton has said the effective friction angle along the joint should be defined by this JRC log 10 by JCS by sigma n. Okay, here if you see the what is the terminology, phi b is the basic friction angle, sigma is the effective normal stress, JRC is joint roughness coefficient. So what Barton has said for this JRC, you see some tables, okay, some lines. If you find these lines like that, I should put the value of between 0 to 2. If you find the roughness like that, 14 to 16, you have to put the value. These lines are subjective, okay, but he has given the unique way to find the toe along the joint. JCS, what is JCS here? This is a compressive strength of the intact rock. Okay, if rock is weathered, then I will take sigma c by 4. All is all this sigma c by 4 are empirically driven, okay, by the researchers' data. Okay, so what to remember here? Again, have to remember what is the effective friction angle, this term, and JRC is given by this Barton 1976. Okay, here JCS is your compressive strength of rock. Sometimes you have to find the JCS with the Smith-Hammer test. Later on we will do the test. Okay, so not be confused. You just find out there is a two equations. One is given by pattern, another given by the button. So you have to remember all these things. Okay, fine. Have you got something?
Yes, sir.
Yes, sir.
Okay. So if you see the apparatus, direct shear apparatus, what you will use today, if you see is very carefully. So this is some unique type of, I can say, apparatus. Okay. So if you see the video, then you will got the point. But what you have to note down, there will be one vertical load cell, one horizontal load cell. Okay, why? Because I want to, because if you see these pictures, okay, see these pictures, okay, so something I have to put on the top of the block. So that will be the vertical load cell should be there, and I have to push this block. The lower one will be the fix, upper one will be in the shearing. Okay, in our setup you see in the lab, okay, the lower one will be the in the shearing mode, upper one is the fixed. Okay, so just I want to make the shearing here now. What is my aim? I want to make shear, the frictional resistance I want to find. So what is the capacity? If you see the shear load capacity, the horizontal load cell has the 50 kN. Normal load capacity is again, this is given the capacity of that load cell. Okay, then the maximum horizontal displacement, how much shearing has occurred linearly, okay, that we have to find. Okay, maximum vertical displacement I have to find. Why? Because if you see the joint now, how to make you understand, see it will dilate. Okay, later on I will explain. Okay, later on I will explain this point. Okay, how it dilate. Okay, and shearing rate, if I am pushing the block over each other, there should be some fixed shearing rate should be there. Okay, if you see in the video, okay, what is there, okay, like this is the shear load cell. Okay, this is horizontal LVDT for measuring the how much shear displacement has occurred. Okay, this is my shear box. This is vertical LVDT. Okay, how much the vertical displacement, because when the it will sliding will occur, so it will ride on the roughness. So these are the all things are there to make our purpose. Okay, so if you this setup, then again things, I hope the things should be clear. What is here? This is shear force, as I talked in the last slide. This is, I'm putting the shear force here. This is normal force. This is my joint sample. Okay, joint sample here. Okay, and this is, I am given some bearing. Okay, there will be no frictional resistance because I want to make shearing now. Always remember the shearing should occur between these two planes. Okay, so I should give the some arrangement here. Otherwise, what will happen? The shearing will not occur here. Okay, it will add on. So it should be the frictionless bearing should be there. Okay, so here is the horizontal load cell. So what will be the normal force? Sigma n, this and force by this area. What is this area? If I say 10 centimeter into 10 centimeter, so that is my area. Okay, what will be the shear force? Is written T by A. Again, A will be 10 into 10 because this is the along the plane. I am talking about along the plane. This is the normal setup. Okay, now if you see this figure, I'm talking about this figure. This is the my joint plane. Okay, suppose this is the joint plane. Okay, the block, this is the joint plane. Okay, so what is written here? I'm encapsulating this joint plane. Okay, to make our testing easier. Okay, like plaster of Paris. What I did, see in this figure, this is my joint plane here. Okay, surrounding, I put some plaster of Paris, make it hard. Okay, so I can fit in the box, 10 by 10 box. Okay, so some encapsulating material we have to use. Okay, to make it shear. Okay, in video you will see how to make it. So what is written as per ISRM, the shear displacement should be in between 0.1 to 0.2 mm per minute. Okay, this is the standard. Okay, we cannot make 5 mm per minute. Okay, it should be at max 0.2 mm per minute. usually suitable for the whole test, although it can be slightly increased 0.5 mm per minute after peak shear strength. When the peak attended, we can increase this shearing rate. Okay, I will show what is the peak and all these things in next slides. Okay, now if there is a joint has some clay coating. Clay coating means suppose there is some filling material there in the joints, then I can use this type of shearing rate. Okay, because what is the meaning here? If you change the shearing rate, okay, your toe, okay, shear strength will also change. Okay, so you got something from this slide? I think some questions should be there from that side.
Yes, sir.
Yes, sir.
So for the shear force, sir,
Yes.
for the value of tau, sir. So we
Yeah.
will have some different area other than the area which is used in normal force.
Yeah,
Because
yeah.
that the shear force is not acting on the same area. Maybe this is acting, but I think it should be T by some other area.
Yeah, we always take the nominal area. What we are saying, this is the roughness. So you are saying that the area is not 10 by 10. You are telling like that, na?
Yes, sir. For the normal force, it should be 10 by 10, but for that shear force, it should be different because the
Different. Yes,
because
it
that
should be different. Okay, but what we do, okay, this is we always take nominal surface area. Okay, so here we have to take again 10 by 10. Okay, then otherwise what will happen, we have to do the some calculation. So for in this test you have to take 10 by 10 nominal surface area. This A is nominal surface area. Okay, if you want to do, you can do some equations already developed in the literature, but here in the this lab you're taking the nominal surface area. You got it?
yes, sir.
Anyone, please ask the question.
Sir, in the third figure,
Yes.
we have a cylindrical sample here for testing.
Okay.
So, like, is this a single sample for testing? Like, from the picture, it can be seen that like the like both of the surfaces are polished so that it can be smooth. So, if we do that, then we will lose the uh, cohesion term and the friction term.
Polished where? You are showing these are the polished. Ye wala.
Yes, sir.
Okay. Suppose there's a one term now. If you see here, if I want to calculate the phi b, how can I find the phi b? Then I have to so cut the roughness. I will totally remove the roughness.
Okay. Yes, sir.
Okay,
Yes.
then I able to find this phi b now. Otherwise, I am not able to find this phi b. That's why this is you are seeing this picture. This is the smooth. You getting?
Yes, sir. Yes,
Anyone?
yes, I got it, sir.
Some more questions should be here. There. Please ask.
And sir, like in the first two figure, is there any difference if we keep the sample like in the first figure we have a like cubic type of sample, and in the second figure we have somewhat like tilted, like it is a cross sectional is looking like a parallelogram. So will it create some difference, or like
No, no,
is it?
we have to take this nominal area. Okay, that's all. Okay. You want to say this is the, like this sample is like that one, another sample is like this type of sample. Okay. So is there any difference? You want to say?
Yes, yes, sir. Like I thought like it might be some kind of, it creates some kind of
No,
difference.
no. Whatever the area, I take this area. Okay. I take the pi d square by 4
Yes,
this
sir.
area. Okay, because
Okay.
the toe is your t by a nominal area.
Yes, sir. Got it.
Okay, keep in mind the one the if I the from our laboratory, if I say the upper block, because there are two blocks now, the upper block will be fixed, the lower block will be slide. Okay, then there will be shearing will occur na, otherwise there will be no shearing. So
Yes.
please keep in mind. Okay, so if you see these, try just the mechanism what is happening there. Okay, I'm just giving you, if you don't understand, don't worry about it, but try to understand what is happening there. Okay, suppose this is upper block, this is lower block, this is my fixed, I make it fixed, this is the roughness. Okay, I take the roughness. Okay, so what is happening, if I'm making toe, so some delta d displacement should be there. Okay, so what will happen? What will happen by this delta D? Anybody can tell me? What will happen?
The upper block should move with respect to the lower block. Like
The upper block will ride somewhere, okay, because there is some angle, na? This expertise has some angles, okay. This expertise, this, so upper blocks start some riding, okay. That this is called vertical displacement del V. Okay, for this we have the vertical LVDT in the system to measure this how much this block is going up, vertical displacement. Okay, it will happen for the small delta D. D is your displacement, shear displacement. If you see later on, what will happen? Again it will, the sigma n is there, again it will, again there will be some vertical displacement. So what will happen in this course of shearing? I can say some expertise will be sheared off. Can be possible? Some expertise can be sheared off at the
yes,
larger
sir.
displacement. Oh, sorry. At the larger displacement, it is possible. Some
Yes, sir.
tension crack can be there and it can be sheared off. If you see very carefully this graph, see, if I am talking about shear displacement D and this is shear stress. Okay, so what the graph will be like? It is going in that way and it is somewhere. This is my, this is peak shear stress. This is called peak shear stress. Then it should be down. Why it is down? Because the expertise are failing. See this D figure. The expertise are failed here. So it will attain the residual shear strength. So I will say this is tau R. This, so here I can say tau P is around 1 MPa. Then tau R I can say around 0.7 MPa. This is the residual shear strength. Okay, if I take the slope of this line, if I take the slope of this line, this is called KSS. What is KSS? This is shear stiffness. What can be unit of this shear stiffness? Can you tell me from here? From this graph, this is in MPa. This is shear displacement in mm. What will be the unit of this KSS? Anyone? What I'm asking here, if I want to take the slope of this line, okay, this is the MPa and here is in the x-axis there is a mm. So what will be the unit of this KSS, shear stiffness?
So it's normal MPa by mm or MPa by meter.
So the unit should be MPa per mm. So what is the physical meaning of that things? If I say the cases coming 5 MPa per mm, what does mean? For 1 mm I have to apply 5 MPa shear force. This is the meaning. Okay, these cases. So we should know. Okay, for the 1 mm, what should be our the shear force? Should be there. Okay, and this is a very important parameter to put in the numerical modeling that you learn later on. Okay, so what is the cases? The slope of the graph between shear stress and shear displacement. Like you find the elastic modulus na in UCS in last class. So I have to find the slope. This is called KSS. Here is the mm. This is the shear displacement. Okay, so what I found the three things from this graph. One is my peak shear stress. Another is residual shear strength and KSS. Okay. Now, as I told you, we are also interested in the vertical displacement because there is a roughness. Now, if you see the joint, there is a roughness. So there will be some vertical displacement. So I was interested in the vertical displacement. So if you see vertical displacement, dilation. Basically, if I say dilation means the change in volume. Okay. If you are you able to see here, your upper sample is going up. Okay. So the sample volume is changing. Am I right or not?
Yes.
Okay, so dilation means the change in volume. Okay, so if you see this graph, if you plot this graph, so initially it will be in contraction mode. Some negative values will be there. Why? Because you are putting the sigma n. based on the sigma n, this expertise will be closed. Okay, there will be some aperture. If you see the definition of aperture, the gap between the joints, okay, the vertical gap between the joints, it will be closed. There should be some contraction. Okay, the some data will be the negative. Then as soon as it start riding on the expertise, then it will take this path. Okay, so it is my positive displacement. This is my positive displacement. This is my negative vertical displacement. Okay, so how to find the dilation angle? What you have to do? You have to find this peak shear stress, put one line here, and you have to find the tangent here. The slope of that tangent gives you dilation angle. You have to do all these things in the Excel. Okay. What you can do, because this is a straight line now, so you can find the slope of this straight line. It will give you the dilation angle. That will be the average dilation angle. Have you got what?
Yes, sir. Got it.
कैसे निकालोगे डायलेशन एंगल?
So can you repeat how to take out dilation angle?
1 minute. I have to थोड़ा मिटाना पड़ेगा. ठीक है, नेक्स्ट इसमें what is here? This is the peak shear stress is there. Okay, if I put the vertical from the peak shear stress, it will come somewhere else. Okay, if I draw the tangent on this vertical on this line, okay, and I take the slope of that tangent, it should be my dilation angle theoretically. Okay, but if I give you data, so data will come in that fashion. Okay, let me explain you here. Okay, data will come in. This is, suppose this is your graph. Okay, just you see this graph. Okay, you see this graph. Okay, here is something where is the peak. Okay, if you draw the vertical somewhere else, so I can take I can find the slope of this line. Yes or no?
Yes, sir.
In Excel. Okay, so that slope will be give my the average dilation angle. Okay, what we are doing slope. Okay, as per Barton. Okay, as we discussed the Barton theory, now what Barton has said, your peak dilation angle should be corresponding to your peak shear stress. That's why putting the tangent here corresponding to peak. Okay, I will show you. Okay, how to find it. Okay, don't worry. So I think dilation is clear somewhat.
Yes, sir.
So can you repeat why dilation is negative at the start?
Yeah, good question. Okay, suppose what is happening, if you see the previous slides, you see I'm putting the sigma n. Okay, there is some joint plane is there. Okay, I'm putting the sigma n. So if you see the joint very carefully, if you see the joints now, it had some aperture. Okay, have you studied aperture? You know what is the aperture? The vertical distance between the two joint plane. Okay, it's very little. Okay, you can see in microns. Okay, as far 1 mm in mm, you can say. Okay, so what will happen when I applied the sigma n? It will close. It will close or not?
Yes, sir.
It will close. So if then it will close, then what will happen? Initially, if you are applying the shear displacement, then it will come. The initial reading will come in the negative. That will call the contraction because of the aperture of the joints. Are you getting or not?
Yes, sir.
क्या थोड़ा समझाओ मुझे वापस. Repeat it.
Sir, what happened that there was aperture initially which got closed when we slided it, and that's why dilation got negative.
Okay, because if I increase the sigma n, so your joint will be compressed. Okay, it had some aperture is there. The aperture should be closed first, then it will start riding on the roughness. It's very complex phenomena. Okay, you have to understand in that way. Okay, So initial reading should be the negative, but if you again you further study these things, na, if you keep increasing sigma n, suppose the sigma n is very high, then what will happen? Then there will be this contraction will be not be there. Your graph can be start from the 0 to 0. Are you following these things?
Yes, sir.
Okay, see this. If there is a 1.5, for the 1.5 you see there will be, here is the showing the negative, which depends upon if this is your 0 point. Na? This is, if I draw it, this is your 0 line. Okay, so for the most of the cases the joints are in the contraction because of the sigma n. Okay, so what you have to do in the laboratory? Okay, I will give you some data. Okay, suppose the sigma n, this is the range of sigma n, 0.25 MPa, 0.51 MPa, 1.5 MPa. I will give the data like 0.25, I will give the shear force. Okay, I will give the area, you just convert in the MPa. Okay, and I will give the shear displacement. Three data I will give. I have to plot the graph between shear displacement and shear stress and shear displacement. Okay, you have to plot, and you have to see where is the peak. Here in this graph you can say here. Okay, the some student can say that यहाँ पे भी आ रहा है peak. So always see, if you are doing the graph ना, always take the first peak. Why the first peak? The graph can be like that. ऐसे हुआ, then is something down, then it can be like that again. So okay, so I should take this first peak. Okay, so I will take the peak shear stress. Again, this here is the peak. Again, somewhat here is the peak. So I will write, suppose for every sigma n, this is my peak shear stress is there. Then I have to write the residual shear strength. What is residual? As I discussed, this is the residual at 10 mm. Okay, it's up to you. If you're doing the shearing 15 mm 20 centimeter, that will be your residual. This is my residual value. Okay, so if you see, if you plot this normal stress and peak shear stress in the Excel, so you will get this line. This is the straight line, y equal to mx plus c. So this 0.3065, it is your C cohesion. This 0.993. Okay, so if you convert in the 10 inverse, it will give your phi. You got it? You got it? Are you getting these things or not?
Yes, sir. Yes, sir. Very good.
Hello.
Sir,
बोलिए.
just repeat it again.
Up to
This
here is clear.
one average dilation angle. This one, 0.999 last class.
Listen, if you want to plot the graph between normal stress and peak shear stress, these are the data you can plot in the Excel. 1, 2, 3, 4 data is there. You can plot. If you put the trend line there, okay, there is an option in the Excel. You put the trend line. This is the equation of straight line, na? Y equal to mx plus c. Suppose this is y equal to, what is the 0.009 3x plus 0.3065. So this is your cohesion. So this is the intercept, na? This is your cohesion value along that joint plane. Okay.
Okay, sir.
This is the slope of that line. I want to find the phi. So this is equal to tan theta 0.993. I can find the phi. Yes or no?
Yes, sir.
Okay. So you have to find the phi. Now, have you calculated the residual? Again, I will plot the normal stress with the residual. So this is the same things. I'm plotting with the residual. So here 0.003, the cohesion is very less. Okay, with the residual, and this will be your residual friction angle. So what is your residual friction angle is tan theta equal to, can you tell me, 0.594. So here you are getting the residual friction angle. This is your peak friction angle. Because we are calculating with the peak now. So this will be your peak friction angle. Have you got the things? Otherwise, I have to repeat.
Yes, sir. Got it.
Got it. Okay. Likewise, there will be vertical displacement also given to you. You have to plot the graph between vertical displacement and shear displacement. This is simple plotting. Okay. So, 1 minute. What next? Okay. So, if I put 1 minute. Okay. So, what you have to find finally? Okay. If you plot the graph, दिख रहा ना आपको? Are you able to see what I am plotting?
Yes, sir.
Yes, sir.
This is your first graph. Suppose this is your first graph. This is tau equal to shear displacement. Then here again is D. There is a vertical displacement. This is V. So what data I will give? I will give the different sigma n. This is your sigma n first sigma n1. Okay. So you have to see this data. This is your tau P. Tau peak. So this you have to find the peak shear stress. First data. Then you have to find two residual shear stress. Okay, slope of this line. This is your KSS number 3. Okay, then this graph will be somewhat will be, if you plot the data, it should be somewhat here like that. Okay, so corresponding this peak. Okay, I will take this point, so you can take the slope of this line. Okay, from the data I have to plot in the Excel, so I have to find this dilation angle. This is called number 4 average dilation angle. Okay, then number 5 you have to find the cohesion and friction angle, peak friction angle.
So can you explain KSS?
What cases you want? क्या करना है इसका?
So what is KSS in this diagram?
The shear stiffness, the slope of that line. This is called.
No, sir. What?
Yes.
What? It's the distance from the x-axis, or what is it?
I'm not getting what you are asking. Please repeat.
So you have marked KSS on this diagram.
Here.
Okay, sir.
Okay, so this is your called shear displacement, shear stiffness. Okay, so you have to find all these things. Okay, if you want to see the data, please let me know the things are clear or not. I hope something is clear. You got something?
Yes, sir.
Okay, so just
Yes,
we are
sir.
playing video. Okay, just see the video, then things will be more, I think, you more improved. So this is there is no sound, okay, because in lab there is a lot of work is going on now, so intentionally we are not putting the sound, okay, but there is a subtitle. Try to understand. Download किया हो रहा है. Okay, wait for 2 minutes.
Sir, can you go on to the 13th the slide number?
Which number?
13, sir. 13. Yes, sir. So, so we are plotting the graph like the rightmost, bottommost graph, sir. So
Okay,
this is the graph between before the peak point, or just after and before the peak point.
peak point. I'm taking the peak point, like here I'm taking the peak point.
The
This is
peak point,
your peak point.
yeah.
Okay,
Okay.
the video. Okay, then I think
Yes,
1
sir.
minute.
Sure.
It is. Are you able to see
Yes, sir.
video? Okay. Just okay. What is written? Jointed rock sample taken from the drill core. This is the joint. Okay, if you see on the screen now. So this is the joint. Okay, as we discussed. If you see the video, then this is the arrangement of 10 centimeter to 10 centimeter shear box. This is 30 by 30. In between, we are putting the 10 by 10 shear box because I want to test the 10 by 10 centimeter. Try to understand. Okay, I can understand it's difficult to understand, but this is the best way we can survive. This is 10 by 10 box. This is a fitting inside the 30 by 30. This is some arrangement. Okay, we are making some arrangement to fixing the. This is the encapsulation of the plaster of Paris. How we are making the encapsulation in the cylindrical joint sample plaster of Paris. We give some time so it becomes hardened. Okay, like it is like that. Okay, so I can say this is one the lower box, another is upper box. What is written here? Fixing of two holes lower and upper of cylindrical joint sample. NX size is 54 mm in the shear box. Here the joint sample is encapsulated with the plaster of Paris. So again I am fixing. At the fixing you have to be very carefully. Okay, it should be mesh joint. Okay, okay, again there is some arrangement. We have to make it. Okay, so it is there. Okay, so this is your normal load cell. So we are making it fixed. Okay, your upper block will be fixed by some arrangement and the lower block will keep sliding. This is the software. We're putting some data. Here, what I am doing is specimen ID, length of the 10 by 10. Okay, if it's rectangular. Okay, you have to if you are using the cylindrical sample, you have to see the pi d square by 4. Okay, and equivalent you have to give the length and width. Are you getting my point? If the 54 mm is your cylindrical sample, then pi d square by 4, and we have to accordingly you have to give the length and width, equivalent length or width. Are you following what I'm saying? Hello?
Yes, sir.
Yes, sir.
So can you repeat once again?
And then what is the main thing? The normal stress that I putting here 1, okay, 1 or 10 we are using. It should be constant. Why? Because we are doing the test in the constant normal load condition. This is the shearing rate 0.2, and the data will be captured per 10 second. Okay, here is the normal stress. Okay, it will be applied on the joint sample. This is the shear load by the shear force. Okay, horizontal displacement or vertical displacement. These 4 data we have to take it out. Okay, these are some normal state, how to set it, how to release, how to start sharing. These are all the configuration are there.
Sir, like if one data is
Please.
captured, so if one data is captured in 10 seconds, then like how many data we collect and how long this test goes
Because
on?
we are sharing for the 10 centimeter. Oh, 10 mm. Sorry, we are sharing for the 10 mm. Okay, and our rate is 0.2 mm per minute. So you can calculate how much data you will get. For 1 minute we are getting the 6 data.
Yes, sir. So like how
Okay, I will
how
show
much
some
bit?
data, then you will able to see how much data we are getting.
Yes.
Okay, so first you see this is the application of normal load. Okay, suppose you are giving 10 here, so 10 is applying that let is become 10. So later on it will not change. It should not change. She is 99%, 100%. We can tear before the sharing. Now see here, if you see here, this is your horizontal load cell. Okay, this is horizontal LVDT that gives you horizontal displacement. If you see there is a one vertical here. See my cursor, this is vertical LVDT for measuring of the vertical displacement. Okay, so shear box is touched with the horizontal load cell and the rate is applied. In software there is some arrangement how to make it closer. It's called inching. Okay, so now sharing is started. So sharing is started. Now if you see the graph, how it is coming. So here I can say this is the peak. In kg it is given 60 or 65, I can say around 65 kg. This is shear force. Okay, if you see then it will come in the residual. Okay, residual is always less than the peak. So I can say this is the residual around 30. You have to divide by the area to convert in the pascals like that. And this is the dilation. Okay, this is very rough surface now. So this is about the dilation. Okay, so these are the data. Data is keep increasing here. Okay, so we are getting this is the peak and this is your residual. Okay, for this is 1 sigma n. Okay, now if I will change the sigma n, then again the graph will be there. Okay, some different graph will come. Okay, for 1 sigma n there will be one graph. Okay, of shear force, shear stress and shear displacement, like vertical displacement, horizontal displacement. So sharing is finished, then we will make it release. Okay, our data is stored at designated file. Okay, this is vertical LVDT. Okay, so this thing to show one picture is there. The vertical LVDT. See here, what is if you see carefully, the rock joint sample after shearing only small fraction of total area. Okay, because it's the roughness now, the only small fraction of total area is sheared. Okay, not the total area because of the roughness. Okay, so keep in mind, okay, only small area is contributing in the shear stress, not the total sample. Okay, if you can see the white patches, okay, here. Okay, so this is the total process. Okay, what we have done so far. Okay, so any question regarding video? Please. Hello. Any question?
Sir,
हाँ.
can you explain the significance of dilation?
क्या बोल रहे हो? Dilation?
Significance.
Significance. Listen, when the shearing is occurring, you see here in the graph. How can you know what is the roughness? Okay, because if in the process the shearing is occurring, Shearing is occurring on the roughness. How you know what is the roughness? Because in machine you never know what is happening inside. So only the dilation angle, okay, will show us what is the level of the roughness. Okay, if it is totally smooth, then your dilation angle should be क्या होगा? 0. Definitely be loud. So if dn is coming close to 0, it means I can say the roughness is very smooth. Suppose dilation angle is coming 22 and 18 degree, I can say this joint has some roughness. Okay, so the quantification of roughness, that's why physically quantification we have used this dilation angle. Otherwise, you'll never know what is the roughness of this joint. Are you getting what I'm saying?
Yes, sir.
To represent the roughness, we are representing the roughness in terms of the dilation angle.
Yes, sir.
Okay, good question, I will say. Anyone else? Please ask. Otherwise, I will show the data what to do. Okay, so I'm just opening the file of data. Okay, so I think these things are clear. This is your normal stress. I have to write here normal. Normal stress. This is your peak. Here stress that are taken from the graph. Okay, then this is your residual. Simply I did plotting. Okay, in the Excel. First these two, second time these two, and I am finding the cohesion and phi from here. Okay, what I am finding here, cohesion and phi. Clear? If you have any doubt in this slide, in this data sheet, let me know. We will do for the different data. Please ask. Hello.
Yes, sir, we can do it, sir.
Okay.
No doubt, sir.
Okay. Now what is happening? This is the 250 kPa. I am putting the normal load of 250 kPa. Okay. Now you see the data. You are asking now how much data we have. See. This is the time. Okay. Time, you just forget about time. This is the shear load. Okay. And the shear stress. When this is 0, it should be 0. This is the shear load divided by some area. This is the my 90 mm sample is there. So I will give this area of the sample. This is horizontal displacement. This is vertical displacement. How I find the max? Here. Okay, it should be my max. Maximum peak shear stress. What will be residual? This will be residual. Okay. If I take the slope here, it will be my KSS. Okay. Though if you see the graph, if I put it, this is plotted between shear stress and horizontal displacement as we discussed. Okay, if you want to see the data for this month, this is number of data are 2137. I think this is rate is I think quite high. It is not 10 second. It is more than 10 second. I think this data is per 1 second. Okay, so now the next graph, if you see here, this is plotted between horizontal displacement and vertical displacement. So I have to find the slope of this line. Okay, because I have to find the slope of this line. Okay, because this is the peak now. So somewhere the dilation angle should be, average dilation angle should be somewhere here. Okay, so I will take the slope. Okay, you can take slope of this data. Okay, how you will find this data? Anybody can tell me how I will find this data? I have to see the graph of this. This is the graph. So what is the peak? Peak is 0.35. So around 35 I have to go in the data sheet. Where is 35? Here? No, 35 in shear stress. Three. I'm seeing this portion now. This is 3.5. Okay, this is my peak shear stress. Okay, this is, so I will take the data somewhat in here, some data from this side and some data from this side. Okay, then I will plot these two data. Okay, if you plot these two data like the vertical displacement and shear displacement, so I'll get some data. Okay, again I'll make the trend line, the straight line, the slope of this line will give me the average dilation angle. Are you following what I'm telling to you? Are you able to do these things or not?
Yes, sir.
Try it. Okay, try it. Okay, dilation can be cumbersome for you. Try it. Okay, and this is for the next data, the 500 kPa. This is the graph. Okay, see what is happening here. After peak, the expertise are breaking, the roughness is breaking, so it is taking this path. Okay, this is your slope, shear stiffness. So this is your dilation. Okay, dilation means on the expertise your upper block is keeps riding on the lower block due to the roughness. So these are the data. So I will give you four set of data. Okay, four set of data. You can plot it in one graph, like this is 1, this is 2, this is 3, this is 4. Okay, so this will be your peak shear stress. Okay, this is your residual. Okay, everywhere will be your cases. Okay, so we can do like that, no problem. So this is all about for today's. Please ask any questions. Some things should be there. Please unmute. What is the meaning, Mohit Yadav?
Sir, we have to take screenshots of this graph and paste in our PDF.
From Excel.
Yes, sir. Or should we make it on our report itself on paper?
I think you can make the PDF now. Whatever you making the graph, you just make the picture, put in the your Word file, make PDF and upload now. You want to take the snapshot?
Yes, sir. I was asking whether we can take a screenshot or not.
Yeah, anything is okay, I believe, right, Professor? Yes.
Okay, you can do, but it will be better. Dekho, what I want to say, the dilation angle should come differently for all of you. Okay, because if slightly data, this depends how we are taking the that slope. So if you are copying, then I will know dilation angle same आ रहा है, मतलब तुम लोग गड़बड़ कर रहे हो. So you do whatever you want, but you have to find a lot of things here. I think the things are clear. Mohit, why you write, sir? Please unmute. What is the meaning? Mohit is there? क्या मेरा आवाज नहीं आ रहा था क्या बीच में?
आ रहा था.
Then what is the meaning of unmute? So any question?
Sir, I am having a question, sir. Sir,
Bolo.
so I was thinking that if we are bringing a full length of a rock, and we are having we are knowing that there is a distance between them, or maybe there can be a that fault between them. So I was thinking that we are making a experiment that we have to break the rock itself. But in the video or like the experiment you have to perform, so they are already been broken.
Yes, joint is a naturally occurring phenomena, na? How can you break नहीं करना है rock को? I think you're not getting the definition of joint. Please, okay, I will make you understand. आपने कोड ड्रिलिंग पढ़ा है? पढ़ा है आपने कोड ड्रिलिंग?
No sir.
No? क्या पढ़ा है? Listen, दिया आपका सरफेस है and under the earth These are some joint set are there. Okay. Then if you're making the drilling, so what will happen? If you're making the drilling, so if you're making the core out of it, so what will happen? ये joint आएगा coring के साथ में. You will get this joint or not? Yes or no? नहीं आ रहा समझ में? फिर समझाते हैं, रुको और सिंप्लीफाई करते हैं. सपोज ये एक जॉइंट सेट है अंदर में, ऐसा कोई जॉइंट सेट है अंडर द अर्थ, ये आपका सरफेस है, आपने ड्रिलिंग किया, व्हाट यू विल गेट? इफ यू आर गेटिंग द कोर, सो यू विल गेट दिस टाइप ऑफ रॉक. यस और नो? मिलेगा आपको ऐसा रॉक? हाँ या ना? शोभित नारायण त्रिपाठी, फॉलोइंग व्हाट आई एम सेइंग? हेलो त्रिपाठी, हेलो, am I audible?
Sir, I guess he is facing some network problem.
Okay, so I'm explaining. So I'm talking about this joint. What is the shear strength along this joint plane? Okay, we are not breaking the rock. Okay, this is the naturally. If you see the video, we are the first first one or two. Okay, so this is the natural occurring joint. Okay, we are not breaking the rock. I think it is clear. Most of you.
Yes, sir.
Any question?
So what is the mode of failure for this experiment?
Mode of
failure, sir.
Mode of failure. First, you tell me what you understand by mode of failure. How the rock is breaking? This is the meaning of that.
No, sir. I mean, how experiment can give errors. So,
how the experiment?
What can be the errors in an experiment? We have to write that in our lab report. That's why I asked.
Okay. What is happening? The errors. Okay. I think it's good question. Okay. So listen. 1 minute. There's some slide I should put here. Okay. Suppose this is your joint. Okay. This is your joint surface. Okay. I'll say this is lower block. This is upper block. So I'm saying this study for the matching joint. Matching joint means this should be perfectly matched. So when we're doing the testing now, so we sometimes, most of the times, I can say if you do the negligency, the surfaces are not matched, they are mismatched. Then it is not like that we are doing the matching joint. Okay, we are considering the matching joint, but we should be very careful to make the matching joint, because if you see in the video what we are doing, we are putting lower one, then upper one. So there is a possibility it can be unmatched. Okay, this is number 1. Number 2, anybody can tell? Otherwise I will tell. क्या हो सकता है? You have seen the video. If I'm making the graph, okay, this is the perfect graph. So what is happening? Sometimes graph is come like that. Okay, again it will rise. Okay, so what I said, we have to take like that. We have to take the first peak. Okay, because what is after that your expertise has damaged. Okay, so you have to take the first peak. So if you are not thinking very carefully, so we can take the second peak. So ideally we should not take the second peak. Ideally you take the first peak. So these can be some error in your analysis also. Things are clear? I think you can write too. And you think what can be others? It can be in the reading of the horizontal displacement. Suppose your LVDT is not doing good job. Okay, it had some defects. Then it can be a problem. What is the full form of LVDT? Anyone? LVDT कोई बता सकता है? Nobody?
So it is.
This is linear variable differential transducer. Okay, used for measuring the displacement. Okay, any more question? Sanskriti Lohitya Vasnik. Any question?
No, sir.
You
No,
got all the things? So, okay, Ragini,
Yes, sir. So, for finding the dilation angle, so should we find the slope at one point, or should we find the average slope around that point?
average slope angle.
Okay.
Average slope angle, because the straight line you are plotting na, so it will give the average.
Okay, sir.
Okay, you try it. If any problem, you just ask. Okay, put the in MS team. The dilation angle can be difficult for you, but I think if you do it, then it will come. The value should be around 10 degree, 12 degree. Okay, it cannot come 45 degree, 15, 16 degree. Okay, it can be. Okay, so you can always find the answer. In this range is always fine. Anyone? Where is Khushbu? She is there? Amit Modi? Rohit Kumar Murmu? आवाज नहीं आ रहा क्या मेरा? Am I audible?
Yes, sir, you're audible, sir.
बोल नहीं रहा लड़का लोग छोड़ो. Okay, so I have taken the attendance. So this is enough for today. Okay, so I will make the assignment. Okay, I will give you that 4 data what I have shown you. Okay, try to do it. If any problem, please ask. Okay, if you're doing wrong, there is no issue, but you try it. Okay, if you have the problem, we can again come online. I will tell you how to calculate it. Okay, so anything else if you want to ask? Otherwise, this is enough from my side. Professor Patel, if you want to add something.
Yeah, no, it's good. Can you hear me? Hello.
Yes, sir, we can hear you.
Okay.
Yes.
Yeah, I was just looking at this, like this report number 2, and few of you guys have not submitted. Anybody here who has not submitted, and what is the problem? Like if you are facing any problem, then I can help you out with that.
So many of us were known that the deadline was 12 o'clock. So.
Oh, 12 midnight?
Yes, sir. Yes, sir. So many of us missed that.
So is it like, is anybody here who has not submitted? Else I can change the deadline.
But if a 1 or 2, then we can see. Okay, let them talk. What is the problem from their side?
Yes, sir. Can you please extend the deadline till 12? We were not aware it's like before class. Because usually, sir, it's till 12 only.
Okay. So how much time you want? Yeah. Iswari Vani. How much time?
Sir, can we get like at least so 6 baje tak extend karwa do. It's just that we have the report, but
okay. Okay, we will do, but keep in mind every time we will not do it. Please.
Yes, sir. Yes, sir. Thank you, sir.
Yeah, if I'm not wrong, I told, right, like before the next class or something. But no worries, we can extend till 6 o'clock. Okay, any other problem, like except this timing thing? Like anything solving the problem or whatever it is. Okay, no worries. So we are we are going to extend that time. Okay, I think we can stop it here now.
So, sir, in the second experiment, sir, there was a huge difference in the third